Okay, so we went through a proof constructing the formula for an ellipse. Now let's actually walk through an example putting it to work for us. So we'll look at 16x squared plus 25y squared minus 128x plus 100y minus 44 is 0. So you'll recognize this as that general form that we saw before. So we're looking to do just a little bit of regrouping, put our x's together, put our y's together, and move the constant to the other side. I'm also going to take the liberty of factoring. So 16 and negative 128 each have 16 as a factor. So pull that common factor. That leaves me x squared minus 8x. So 8 by 16 gets you to the 128. I'll do the same thing with the y's. I'll factor the 25. And we're equal to 44. So our goal is to get it to look like a perfect square over some constant, perfect square over some constant, and eventually equal to 1. So as far as the x's, completing the square, half of negative 8 is negative 4. Negative 4 quantity squared, positive 16. But remember, with this 16 outside, that's really worth 256. Similarly, half of 4 is 2. 2 squared is 4. I'm going to write a plus 4, but don't forget with this 25, that's really worth a plus 100. So I'll add 100 to both sides. Okay, so we have 16 by x minus 4 quantity squared plus 25 by y plus 2 quantity squared is worth 400. So we just divide both sides by 400. So x minus 4 quantity squared over 25 plus y plus 2 quantity squared over 16 is equal to 1. So then the bits of information we can grab from that, our center is at 4, negative 2. The bigger perfect square is under the x's, so that's our horizontal axis will be the major axis. And we would move 5 units left and right from the center. So negative 1, negative 2. And moving 5 units right. 9, negative 2. If you want to kind of see that put to work, just let y equal negative 2. That will zero out this entire term. And then x minus 4 squared is worth 25. So x minus 4 is worth plus or minus root 25, and solve them from there. The faster way is to just count left and right by that number of units. Your author doesn't really write it out too often, but the minor axis vertices are also handy to have. So it would go up and down 4 from the center. So our x value stays the same, negative 2 moving down 4, we're at negative 6. And then 4, negative 2 moving up 4, we're still at 4 for the x, and positive 2 then for the y. As far as our foci, we'll just use a squared minus b squared to give our c squared for the ellipse. So that was from our little substitution we did on the proof. So 25 minus 16 is c squared. So 9 is c squared, so c is plus or minus 3. We'll use the... So we move the foci along whichever one was the major axis from the center. So in other words, it's the x values that will be changing. The y values will remain unchanged. So moving to the left 3, we're at 1, negative 2. And moving to the right 3, we're at 7, negative 2. All right. So we'll do just a quick sketch of this. The red will be more visible. Okay, so major axis vertices, negative 1, negative 2, together with 9, negative 2. Foci at 1, negative 2, and 7, negative 2. Center here at 4, negative 2. And move up and down 4 units for the minor axis vertices. So there's our 4, 2, and 4, negative 6. And then we just connect these guys up with a smooth curve. Okay. So a little bit of calculus on the area of an ellipse. Again, without loss of generality, we're going to center this one on the origin. Shifting a solid shape around in the plane won't change the area contained within that shape. A circle of radius 3 centered on the origin, and a circle of radius 3 centered on 100, 200, both have the same area. Same thing with an ellipse. All right, so we have x squared over a squared plus y squared over b squared is equal to 1. So y squared over b squared is 1 minus x squared over a squared. And we can go ahead and clear the fraction under the y. Y squared then is b squared minus b squared x squared over a squared. So y is plus or minus root b squared minus b squared x squared over a squared. Now we can do a little bit of factoring with that as well. Each had a b squared involved. All right, so the idea here, again, we're centered on the origin. This one I'm just going to do just a quick rough sketch. Because an ellipse has two axes of symmetry, we can basically just look at the top right quarter of it and go from there. Now, how far out that goes out to A. So then our total area, 4 times the integral from 0 to a of, since we're in Q1, we'll take the positive. So square root of b squared by 1 minus x squared over a squared times dx. All right, so we can get a common denominator here. Also, square root of b squared, we can turn that into a b, and we can factor it out since it is a constant, not a variable. So area is 4 times b times integral from 0 to a of, let's get a common denominator going there, so a squared minus x squared over a squared. So 1 is the same as 1 over 1, which is also the same as a squared over a squared times dx. And all of that is under a square root. Again, at the bottom, square root of a squared is just a. So our area is now 4b over a, integral from 0 to a of square root of a squared minus x squared times dx. And then we can just do a nice little trig substitution on that. So let x equal a sine theta, then dx is equal to a cosine theta d theta. So in our area, 4b over a times the integral from, since we already have a's and b's floating around here, I'll just arbitrarily use p's and q's for my endpoints until I translate it back. Square root of, so we have a squared minus x squared. So a squared minus x squared is a squared sine squared theta times dx, which is a cosine theta d theta. Again, we can factor out an a squared, and square root of a squared is a, and that will cancel with this a out here. So our area is now, make sure I'm centered well. Okay, our area, 4b, integral from arbitrary p to q at the moment, square root of 1 minus sine squared theta times a. Now this a that we have down here, we can bring him out front. The a squared that we took the square root of, managed to cancel that one, but we do still have 1 left over. So we have 4ba square root of 1 minus sine squared theta times cosine theta d theta. So our area, 4ab, integral from p to q, 1 minus sine squared is cosine squared, square root of cosine squared is cosine, so we have cosine theta d theta, or cosine squared theta d theta. And we can use our power reducing formula on that. So integral from p to q of half plus cosine 2 theta over 2 times d theta. So our area for alpha bravo, antiderivative of 1/2 is 1/2 theta. We'll also factor out the 1/2 there. Antiderivative of cosine of 2 theta would be 1/2 sine of 2 theta. And we'd evaluate that from p to q. Then we want to put our originals back in. So x was equal to a sine theta. In other words, x over a is equal to sine theta. So theta is the arc sine of x over a. Plus 1/4 sine of 2 theta and theta, remember, is the arc sine of x over a. From still P to Q. Oh, my apologies. We switch it back. So from 0 to A. My apologies there. 0 to A now. Okay, so a little bit of plugging and chugging. I'll let you fill in some of the detail work from there. We have the sine of an arc sine and so on. So we end up with area is equal to A times B times pi. So again, I encourage you to kind of see what happens in the middle. See for yourself what happens in the middle. The circumference of an ellipse, basically, we would generally use some approximations to get there. So basically, same idea. You use the stuff happening Q1 and then quadruple it. However, that is, as I said, not necessarily an elementary integral. You'll end up with c equals 4 integral 0 to a square root of 1 plus b squared x squared over a squared minus x squared times dx. So the author has you play with these a little bit, not terribly much, not a lot. Hyperbolas, similar to an ellipse, just flip the sign. Basically, the absolute value of the difference in distances between foci. So the idea is you get a picture of something like this, and call that distance 1 and that distance 2. Absolute of d1 minus d2 is fixed. So basic setup. If we have x minus h squared over a squared minus y minus k squared over b squared is equal to 1, you'll have hyperbola opening left and right. If it's y minus k quantity squared over a squared minus x minus h quantity squared over b squared equals 1, here you have a situation where you're opening up and down. One little note on these, unlike the ellipse, c squared, instead of being a squared minus b squared, is a squared plus b squared for these, for finding the foci. All right, so we'll put some of that to work. Let's look at doing a 4y squared minus x squared is 16. We want it set equal to 1, so we'll divide both sides by 16. So y squared over 4 minus x squared over 16 is equal to 1. Okay, so inside we don't have any shifting going on, so our center here is on the origin. By the fact that it's a y squared minus x squared, this tells us we're opening up and down. So here, a squared is 4, b squared is 16. So our foci c squared is a squared plus b squared, so 4 plus 16. So c squared is 20. So c is, that would be what, 2 root 5. Approximately 4.47. So when we're doing the sketch, we'll go about 4.5 units in either direction. Now, one other thing the author has us occasionally measure, the eccentricity. Unfortunately, they do use a lowercase e for that. So in this context, when they're talking eccentricity and you see a lowercase e, they're no longer talking about the special 2.718, etc., not the e to the x kind of function. Eccentricity is just c divided by a, and that's really just kind of talking about how bowed is it, how much curvature are we looking at. So in this case, c was 2 root 5, and then a was 4. So it would be root 5 over 2. Okay, so as far as how to sketch that, we're going to relate a little bit to what we did with the ellipses. All right, so our center was on the origin. Now, in this case, we don't have major and minor axis vertices. If you set y equals 0, that drops this term off, but you can see if you multiply both sides by negative 16, you get x squared is equal to a negative 16. That kicks us off of the real numbers. So our vertices are just going to involve, in this case, the y. So they'll be going up and down 2 units. So that would be at 2, 0, up and down. So 0, 2, and 0, negative 2. So there's our center. There's one vertex. And down 1, 2, there's the other vertex. So the foci, about 4.5 units each direction. 1, 2, 3, 4.5. And down 2, 3, 4, and about a half. Now, if we were drawing an ellipse, we would be sort of going around here, and we would be going left and right 4 units if this were an ellipse. What I'm going to have you do is kind of go out those 4 units, but instead of putting a dot there, put little dotted lines instead of a point. So 1, 2, 3, 4 units. We'll do just kind of a little dotted line there. And 1, 2, 3, 4 units the other way. And we'll do dotted lines through our vertices as well. You get this nice little rectangle. And the idea is that if you want to sketch this graph, ruler here, what you'll do is draw asymptotes that connect the corners of the rectangle that you just drew. So our curve is going to start at the vertex and it will approach the asymptotes. So in blue there is our actual graph of this function. So again, we're still using the denominators here to help us out, but instead of connecting them with an ellipse, we're making a box around where the vertices would be. All right, so in section, this was 10.1, I would try out 1 through 8 all, and 9 to 63 the odds. If you have any questions, please get in touch. Otherwise, I'll see you next time. Stay safe.